This video is about the correct placement of cutouts in engineered wood I joists. We will be discussing the negative implications of improperly modifying the I joist, which includes financial losses, delayed schedules, and a reduction in structural integrity. Engineered wood I joists are quickly replacing dimensional lumber joists and are becoming the industry standard as they are more effective and efficient. This introduces many more possibilities in building design for engineers. They come in varying sizes for depth and lengths, minimize deflection, and can be modified to hide utilities that would otherwise require a bulkhead or drop ceiling to be concealed. The issue at hand being looked at is the incorrect placement of a cutout in an engineered wood I joist. As simple of a concept as it might sound, we are finding out through home builders and inspectors that it is an issue, and our investigation will show this. The purpose of this video is to demonstrate and teach the trades and industry about the correct placement of cutouts in engineered wood I joists. The video will investigate correct placements via theory and through experimentation. We will only be looking at engineered wood I joists, but the concept of correct cutout placements in I structural members does apply to steel and concrete I members. Also, we will only be looking at cutouts in joists, not beams. Modifications to beams, both drop and flush, are highly discouraged. If it is absolutely necessary, then an engineer must be consulted.
We investigated how much the incorrect cutout placement was an issue by looking at graduates' opinions, contacting the industry, and chatting with city inspectors. 201 students were surveyed from civil engineering techs, plumbers, and HVAC. Not one single person surveyed attained 100%. These are going to be the new hires that will be going into the field and making a first-time mistake. The residential construction industry was reached out to, and it was found that the biggest issue they have is the top flange being nicked. As such, we wanted to show the dramatic effect of what happens to a nicked flange.
The impact from incorrect cutouts in EWIJs can be broken down into costs, schedule, and quality. There are costs in repairing or replacing the damaged joists. An engineer has to be retained to assess the damage, a carpenter has to fix the issue, and time is taken away from the other trades as no work can commence on the subfloors above during the repair process. The trades have to remove any installed utilities in the joists and replace them correctly once the repair is finished. And there is lost time involved as contracts are prolonged and equipment rentals are extended. Often the trade will eat up the cost of the damage. The fix can cause a delay in the schedule by 1 to 3 days. Other trades cannot enter the building as the floors are being repaired. A small delay can cause a rearrangement of the booking of trades, creating more work for the construction manager and causing future scheduling conflicts with the trades that are expected to be working on the next job. Besides the loss of structural integrity, there are other impacts to quality. The trade that made the mistake can have their reputation tarnished and ruin business relationships. Repaired joists also look imperfect to the new home buyer, and they will question the builder's capabilities and the integrity of the structure.
The loss of structural integrity of the joist from incorrect cutout placement can be explained scientifically. We will be brief about the subject. The loading of a joist is calculated through its tributary area and types of loads. The loads are given as a pressure. The loading can be expressed as a line load, as seen in the diagram. It is assumed that the joist is a simple beam. A shear diagram can be created for the joist, and a shear stress diagram. Shear force is like separating the material, like a pair of sheet metal shears. As it can be seen, shear is the greatest at the bearing points, and the shear stress greatest on the web. From this, we can conclude, for a cutout, it would be best located near the horizontal center of a joist where forces are minimal. A bending moment diagram can be created for the joist, and a bending stress diagram. Bending force is like bending a copper pipe. As it can be seen from the bending moment, it is the greatest at the center, and the bending stress greatest on the flanges. From this, we can conclude that for a cutout, it would be best located near the vertical center of a joist in the web. The deflection of a joist can be seen in the diagram. When you bend any long member, you can see it flats. Designs are set with a mass deflection value, which is measured in the center. The experiments will look at the effects of cutouts on deflection. In conclusion, we can deduct that the best location for a cutout would be the dead center of a joist. Cutouts can be made away from the center, however, the further away from the center, the smaller the cutouts must be.
There are several rule of thumbs for hole cutout locations. We will go over some of the most common ones. However, it is recommended to go by the manufacturer's tables. The middle third rule of thumb works as follows. Any size cutout can be made within the middle third of the joist span. The foot for every inch method works as follows. For every inch in the diameter of the hole, the location is moved a foot away from bearing. For example, a 3-inch diameter hole would be located 3 feet from bearing. The diamond method works as follows. A diamond is drawn with the points at each end of the joist and at the center of the joist. Within the diamond, a cutout can be made. For multiple holes, the rule of thumb is from one cutout edge to the other cutout edge. The distance will be twice the hole size. This could lead to a cutout outside the safe area. As one can see, there are many rules of thumb, with conflicts between the different methods as shown with the hatching. Which one should you use? The answer is to use the cutout tables. Manufacturers have tables for cutout locations and sizes. This provides the best results for structural integrity. One must look at the manufacturer's specific table, as they are different from one another. They can be found stapled to the joist when they are shipped out, or in the manufacturer's website.
The setup for the testing of the joists was done in SAIT's Aris Lab. The testing rig has 5 hydraulically powered pistons that are evenly spaced, simulating a line load. Normally, joists are laterally braced by the subfloor. A brace system was used here to restrict movement to the vertical plane. To prevent crushing of the joist flange, blocking was added underneath the piston and to the bearing pipe. The pistons are electronically controlled to give an evenly distributed force, even when there is deflection gap in the joist. This simulates a constant line load a floor system would normally be exposed to. The software tracks loading through a loading cell and gives real-time data readings during the testing. Surveying equipment was used to measure the deflection of the joist. 2 different joists were used. However, this report will not be comparing the different manufacturers' products. We are only comparing the effect of the performance of a joist when a cutout is made. The joist depth is 11 7/8 inches and the length is 160 inches, while the actual clear span is 150 inches. The pistons are technically several point loads. However, they resemble a uniform line load. First, they will be loaded to a design limit of 250 pounds per piston, where the deflection will be measured. Once deflection has been measured, the joist will continue to be loaded until its ultimate failure point. We performed the following tests: baseline, hole at center, hole at bearing point, complete web removal, a nicked flange, and multiple holes. Each test will have 3 trials to confirm results.
Now for the part we have all been waiting for, the action. First up is the joist with no cutout, or a baseline. This will be for a reference point from which to measure the mass loading. Let's look at the side-by-side comparison of the cutouts at the bearing versus the center. As one can see, the cutout at the bearing point failed first. The best place for a cutout is at the center. Up next is the complete web removal. This can be common for HVAC runs. It failed at a similar mass loading as the hole at center. A common mistake in the field is to nick the upper flange when drilling holes for utilities through the floor. Nicking the flange has an adverse effect, as it severely weakens the lateral stability of the flange. You can see the flange sticking out, even with the bracing in place. Sometimes, more than one hole needs to be made in a joist in order to run multiple utilities through the flooring system. You can see it failed to a similar loading as the single hole at center.
Now let us conclude our results. The purpose of the testing is to prove the dangers of misplacing a cutout in a joist. Once a hole is misplaced, the best case scenario is that someone has to use extra labor or material to fix the damage. Worst case is the building is left with a structural issue that could potentially put the public in danger. We suggest you always look at hole placement charts or consult an expert when cutting holes through engineered wood I joists. The charts can be downloaded from the manufacturer's website and easily understood by all. Do not memorize one manufacturer's charts and apply them to all. Each manufacturer has different allowances for hole placement. Rules of thumb methods are not always correct and should not be relied upon. We would like to thank Allspan Lumber, Axe Lumber, and D&B Lumber for donating all the materials used for testing. Also, many thanks goes to SAIT for making this possible. Carlo Velchek, Tahir Hassan, Lee Morden, Brandon Poole, and the Eris Lab. A big shout out goes to our industry advisor, Carlo Velchek. Funding was made available by the ISPF program at SAIT.